Hi guys. Today in the second part of SVM we are going to study as mentioned here in depth SVM mathematical formulation of SVM. The objective of today's lecture is to find a hyperplane that does margin maximization. We have to find such margin plane where we can get maximization. Okay, this is the our diagram. You have to be focus my pointer. Here is written we need to find a hyperplane. Our purpose is there to find a hyperplane. Purpose of find a hyperplane to maximize the margin. Okay, yeah, this pi means margin maximization. Yeah, value of this w transpose x plus v equal to 0. W not necessary unit vector. Here no need to be necessary w as a unit vector. Okay, w sigma plus means w transpose x plus v equal to 1 and sigma x equal to w transpose x plus v equal to minus 1. Okay, by simple coordinate concept we can get d equal to 2y magnitude of w because this is the distance is there. So distance is there. Here we have to put value of the w, then we get scalar quantity. Okay, here we so we have to maximize d. Our purpose is there to maximize d. What our purpose is there, you have to keep an purpose in mind. That is why we are going to in-depth study of this. Purpose is maximize d. We have to maximize value of d with the constraint that all positive points will be above 5. Constraint is there. All the positive points will be above pi plus plane and all negative points below this plane. Means clearly separable is there. That means all the negative points or positive point lie this side or this side. Means there is no any exchange of points are there. Means from this point no, they will not lie this region or as well this point of size wouldn't lie in this region. Okay, this is the meaning of this is there. This is our purpose. Keeping in mind this is the constraint. Okay, so the optimization function becomes this hard margin. Yesterday we read about the hard margin, which is the ideal condition is there. Okay, you have to this circle under this circle cross is sign is there means points are there. Value of this and value of the point which lies on this line if this equal to 1, yeah, greater than 1, and value of points which lie on this line is equal to 1 or value which lie this point and below this line equation this points are the support vector which lies on the which support vector which lie on the this line. Okay, this is equation you have to keep in mind. both are equal one. Both are equal one. You not get to be confused with this line equation plus one, minus one. So you might get confused, but you have to even though both are plus one, plus equal to one, equal to one, and this is the support vector because are lie they are lying on this line. Okay, here next. But what if we have a data set that is not linearly separable but almost linearly separable? They are telling such data sets which are not clearly linearly separable but almost linearly separable. So answer is given here. We formulate an alternative soft margin. Then we go through the soft margin. Yesterday we read about this soft margin means which is practical situation is there. That means according to this diagram, some points of this side get enter this in this region, and some points of this side get entered in this region. Means overlapping is there. That means okay, like this. Some points of this side reached this side, or some points of this side reached this side. Okay, so this is to remember here. Here we are taking zeta. This is called zeta. It's the symbol zeta. This is the equation, or we are taking this value from distance of this points from this line equal to zero point 0.5. Okay, and this this we are taking this value from this 1.5. Okay, this is the equation of this. Okay, but these are the this line equation, minus side, positive side. Okay, here is clearly written zeta. G xi tends to zeta I. Zeta I equal to 0 means if this equal to greater than 1 means for correctly classified points. Okay, zeta greater than 0 means it is equal to some unit of distribution away from the correct hyperplane in the incorrect direction. Meaning you have to read about this. Okay, and now we want to minimize these error. Our purpose is there to minimize these error. Exactly. When we minimize the error, that means we are reaching toward the exact, and you can say true value. Okay, now you can say earlier you were talking about the maximization, now you are talking about the minimization. You have to remember this function parameter mind. Earlier when we have to maximize, that will become 2yw. When we do talk about the minimization, this value become w by 2. Okay, this you have to keep in mind. This is the margin, and argument minimum wb margin plus this this is your average distance of misclassified points. This is what is this? This is the average distance of the misclassified points. This term represents this whole term represents the average distance of misclassified points. Okay, and this whole term represents margin. This whole term represents margin, or this whole term represents an average distance. I mean, distance is there, but which distance? Average distance. Of which points? Misclassified points. Okay, or this is also called hinge loss. This hinge loss you can say, otherwise you can say, if you say in interview this is the hinge loss, they will ask you what does it mean. So you have to tell this is the average distance of misclassified points. Hinge loss means average distance of misclassified points. Okay, and is st such that st means such that st the abbreviation of such that. This here c is a hyperparameter is there, mean this c, the term this c is there, this is the hyperparameter. Okay, see the hyperparameter is there. If c value increase mean tendency to make mistakes reduce it, decrease. C value increasing means tendency to mistake reducing, means overfitting. Overfit means high variance. You have to keep, means overfitting is there, means high variance is there. Overfitting means high variance. You can, some of the students get confused to remember. So I would share trick to remember. So you will never forget it. Whenever someone says overfit, you have to remember high variance, means HIV. HIV, you know, this is the disease, but this you can remember by using the high H. H means high, V for variance, or overfit. Fit. Or C reduces means underfit. Under underfitting means high bias. Underfit means high bias there. How to can remember this analogy to about confusion in the interview? The interviewer tried to make you confused so that you can lose, so that you can lose your confidence. But you have to avoid this, avoid to lose confidence. So overfit means high variance, HIV, HIV, high variance. Underfit means high bias. Underfit means high bias. You can remember like this: under D, here B, here opposite in small letter. B and D are opposite of this. So here you have to remember high. HIV means in both the cases they are talking about the high, high. Okay, high. But you have to remember like this: high. You have to first think high, then underfit, under D. D opposite of the B. Mean under is this means underfit में high bias and opposite of high variance in overfit. Okay. Correctly classified points means if points are correctly classified, that means zeta equal to 0. Zeta is equal to 0 is there, that means points are correctly classified. Okay, keep in mind this parameter you have to remember and note it down it with as a points, as a you can say note. This incorrectly classified means points which are greater than equal to 0. If zeta value is greater than 0, that means the points are incorrectly classified. You have to mark star these points. These are the short notes you have to remember. Here, we have to, here is written, we have to maximize 2y w. Same as minimizing this. I told you earlier, if this is given, then we have to maximize. If this is given, then we have to minimize. Okay. Or this is the things is written for the soft margin of SVM. Okay. Now, log loss minimization, hinge loss. This is loss minimization means here we are using hinge loss. Hinge loss means the misclassified average distance of misclassified points. As earlier I have already has shown you. So here is you have to focus this diagram, this line, this clearly, or this line, this hinge loss line. This is the zero. This is the line, and this line, this line. Here, hinge loss plus regularization gives us SVM. You have to. How do we get SVM? Hinge loss through the hinge loss plus regularization. Regularization plus hinge loss, we get this. Okay. Although hinge loss also not differentiable at Z1 equal to 1. This point. Hinge loss, it is not differentiable. But since it is a continuous, unlike loss, 0, 1 loss, we can work around X to work with it. We have to understand this. And Z I greater than means Xi is correctly classified. You have to remember this point. If Zi greater than 0, that means our points are correctly classified. If Zi less than 0, that means our points are incorrectly classified. Okay. And this is the you have to remember hinge loss Zi greater than equal to means hinge loss equal to 0 means hinge loss is 0 means the our points are correctly classified. Zi less than 1, that means hinge loss and our point are not correctly classified. Okay. Alternatively, hinge loss equal to max 0 of 1 minus Zi. This is the notes has been covered from the Andrew and G lecture of deep learning AI. Okay, you need to be focused. It is highly mathematical. Consider a Lagrange duality. They have taken the concept of Lagrange duality to make understand this concept fundamentally and clearly. Okay, so consider a problem of the following form. This okay, and then we define the Lagrangian to be this. Okay, and then here, this means Lagrange multiplier to find the Lagrange partial derivative to 0. This, okay, and solve this and this. Consider the following optimal optimization problem means primal optimization problem. You might get confused this term. This is R. So this is primal optimization problem. Okay, you have to be noted down this, and this here they have written to solve it we started by defining this generalized Lagrangian. This is the generalized Lagrangian formula. Are you getting? This is the generalized Lagrangian formula. Yeah. If you are getting any background noise, please, I apologize for this because there is a marriage is there. Uh, that is why you might get little bit background noise. So please bear with me for this. And this is term you have to consider, and this is the consider. Let's move, converge this and this, and let's move. I am going to share only those points which are important for the point of view of interview as well as your basic fundamental understanding. But you have to remember this point. Always remember max minima of a function always being less than or equal to the minimum max. Means max minima of a function always being less than equal to the less than minimum max. Means they have max minima, they have minimum max. So they are a maximum minima of a function always being less than equal to the minimum max. Certain condition is there. You have to remember here. Means there exist these so that this define. Sorry. Suppose f and the gi are convex and fine, and suppose that the constants gi are feasible, mean these means there exists some w so that this. You have to remember and try to understand this, please. Okay, these are some points you definitely make you support to understand. There will be key for showing that SVM has only a small number of support vector. Okay, here dual form of SVM is following primal optimization problem for the finding optimal margin classifier. This and that constant as this, and when we cons, when we construct contract lag the engine for optimization problem, we have this, and this you have to remember. I am going to slow that you can see and make your notes. Important points. Now we let's study important points. Means for every xi we have an alpha I. This okay. Some points are there which you have to be remember and understand. So that this kernel trick, replacing this with generalized similarity function. Quadratic programming means the hard margin and soft margin problems are both convex quadratic. Means hard margin and soft margin problems are both convex quadratic optimization problems. Someone might ask about hard margin and soft margin problems. So you have to remember these are both convex quadratic optimization problems. Okay, with linear constants, both hard margin and soft margin problems are both convex quadratic optimization problems with linear constants. Such problems are known as quadratic programming problems. Thank you so much for today lectures. If you have any queries and any doubt regarding this, please do write in comment box, and definitely I will make effort to clear all these concepts fundamentally, so that you can make it, so that you can relate with it your uh, life. So no need to stress your mind to remember this. Thank you so much.